Okay. Uh, Good morning once again. One of those few lectures that we have conducted at 7 o'clock in the morning on Saturdays. Nevertheless, let us start with the last topic. I would say, though we would say it's the last topic of the first semester, by no means it would be the least. Okay? Not merely because of the sheer size as this particular component on the surface of this planet occupies, but its importance, its relationships with the other spheres also. If you remember, during our first few lectures, I did speak about those spheres of life that we have around us in the three forms of matter. In the sense, the solid form, that's the land, the gaseous form, that is the atmosphere, and of course, the liquid form, that is the oceans, or the hydrosphere around us. What makes a difference between the oceans and the hydrosphere? Hydrosphere, I would say, is a more comprehensive term, which would include all that water in the solid, liquid, and gaseous form around us. Oceans exclusively mean that saline section of that particular hydrosphere. What makes it saline? Of course, we have these salts. Okay, where do these salts come from? Well, of course, when we were small, our grandparents used to tell us these stories that there was this very greedy witch who got hold of this gadget which yielded salt, because salt was a very important commodity, and she tried to steal it away. And this was a gadget which kept on yielding salt at a regular pace, 24 by 7. And she took it away on a small boat. And when the boat entered the oceans, okay, it so happened that she lost her way. And while the gadget kept on yielding salt, okay, it gradually filled the whole boat, and the boat sank. And it is believed that this particular salt yielding gadget is still yielding salt at the bottom of these oceans as such. Of course, we now all know that this is more of a mythological, or I would rather say, uh, 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 I wouldn't call it a sci-fi story, but this is some sort of a very weird explanation we used to get, because we all know that the salt that enters the oceans actually is carried away by the rivers from lands, and then it enters into the oceans. Now, the obvious question would be, how is it that rivers in that case are not saline? The reason being that the proportion of the salt in the rivers is much less as compared to the comparative proportion of the salt in the oceans. Though the size being large, because the oceans are say the last resort, or I would rather say the last destination for all these minerals and salts as such, it has kept on accumulating in the oceans for, I would say, hundreds and hundreds and thousands of years. As a result, uh, it has uh, it has stayed to be there in the oceans, making the ocean waters significantly saline. As such, we will be speaking about the salinity of the oceans as such. Along with the oceans, okay, the importance of the oceans, we also would be speaking about how these oceans tend to be significantly important as far as climate change, etc., is concerned. Not that we would have the time to go into all the discussions of oceanography as such, basically, because we are doing it as one small single chapter in your syllabus. While if I would to elaborate it further, okay, at our PG levels, postgraduate levels, we have separate papers, each on geomorphology, each on atmosphere, and each on oceanography. And to go further, okay, you would have centers. Say, for example, the SP College PG Center has a specialization in geomorphology, wherein we would go into further detailing as such. Though we don't have specialization in climatology, we do have a specialization at the university department, if not the SP College as such. And As far as oceanography is concerned, there are departments which would have specialization in oceanography. We have our own Indian Institute of Oceanography in Goa, which offers you masters in oceanography as well. So what I mean to say is we are going to do a small tip of the iceberg, or rather, we have been doing tips of these icebergs, which is a basic requirement for students of FYBA, I would say. What you see in front of you is basically the stages how the world waters got divided into various oceans as such, and you'll see the change as to how these tend to happen. We would first start with the world ocean. All the waters together is the world oceans. Okay, everything that is beyond the scope of land surface is considered as ocean waters. Okay, in some regions, smaller parts of these oceans tend to be classified as sea waters as such. Okay, a sea is normally a smaller section of a larger water body, water mass, which is called as the oceans as such. A world ocean could further be presently divided into five major oceans, I would rather say. Okay, and which all are these five as such? You can see them in front of you here. Okay, I will try to pause it. Sorry, this is the world ocean, and one by one we will go into the detail. The largest of the oceans, of course, is the Pacific Ocean, which you can see towards the south of your slide as such. And then you have the Indian Ocean towards the right of your slide, the Atlantic Ocean towards the north of your slide, and of course, what we called as the Arctic Sea once upon a time is now called as the Arctic Ocean. An interesting development which took place around 2006, that's around 15 years ago, is that the World Oceanography Institute or the International Oceanographers Organization, they started discussing about a new possibility that they would be required to be taking up, and that was the addition of the fifth ocean. Now, what was or which was this fifth ocean to be? This fifth ocean was to be the Southern Ocean. Okay, it is that ocean that you would tend to see in towards on this very slide. Now, there is a very specific reason why oceanographers have gone into identifying this as a new ocean as such. Okay, you'll see that when we say a new ocean, it does not mean that there have been very many geomorphic tectonic movements which has led to the formation of a new deep sea plane, which has now been called as the ocean as such. In fact, you'll see that unlike all the other oceans, okay, this ocean that you are going to see here, okay, just check the name of that particular ocean that is now called as the Southern Ocean. Now, if you see the boundaries of the Southern Ocean, it's very interesting. Okay, you'll see that the boundaries of the oceans are circular. Okay, this particular ocean is circular, and it is an ocean which has been carved out of the rest of the oceans. Say, for example, the southern part of the Indian Ocean, the southern part of the Pacific Ocean, and the southern part of the Atlantic Ocean, so to say. Having said this, why, okay, or to start with, what is this? What is the dimension of this ocean, or rather, why is the dimension of this ocean circular? Okay, it's basically because all those waters which are beyond 66 degrees, 60 degrees south, 60 degrees south onwards, okay, till the shores, let us say, of the Antarctic continent, all these waters came to be labeled as the Southern Ocean. Any specific reason we were required to identify this ocean as separate ocean? Yes, definitely there are reasons, basically because the waters around the Antarctic continent, this year is the Antarctic continent, by the way. Okay, if I can relatively give you a sense, we are looking at the southern ocean, southern pole, or the southern hemisphere, not exactly the southern hemisphere, but we are looking at the Earth from the south. Okay, you can see this is the South American continent, this is the African continent, and here you have the Australian continent as well, and you come up here. From here, you'd come to Asia. Okay, so the reason that we were required to, or scientists suggested that we should be having a new Southern Ocean, is that the temperatures on the continent of Antarctica will obviously make an impact on the waters of, say, the oceans around the continent of Antarctica as such. And it so happened that it has been noticed that it has an ecosystem of its own, with very I would say cold waters circulating around the Antarctic continent as such. It has its own ecosystem. It has its own impacts as far as world climates, local climate, of course, and of course world climate and climatic patterns are concerned. Not only climatic patterns, you would see that drifting of ocean waters into different directions is also to quite an extent controlled by these very cold waters as such. We are going to see a small slide of this at a later point of time, a cross section of how waters move. But because of the importance of this isolated system, okay, though isolated, its impact on other waters of the world, it was felt that we should be having a separate ocean as such. And eventually, as I said, 2006, we labeled this as the Southern Ocean. The moment we called this the Southern Ocean, though it's very small in size, we had again rechristened the name of the Arctic Sea into Arctic Ocean as well. So we'll see that the Arctic Ocean and the Southern Ocean, as compared to the other oceans, the Atlantic, Indian, and Pacific, are very small. But since they are huge as compared to other interior ones, I would definitely call, we would be required to be calling them as oceans as such. With this small introduction, let us move into having a proper, the normal scenario, the normal picture of the oceans that we normally tend to see. And this is basically the ocean currents. Okay, you'll see that we have studied this at an earlier class also, that the world oceans are actually divided by different flows of water, which are called as ocean currents as such. And there are some scientific ways in which we need to understand these ocean currents as such. Before we go into understanding the ocean currents, we can always compare this to, say the so-called pressure systems that you have in the atmospheric layers, particularly the lowest of the atmospheric layer, that is the troposphere. Okay, we saw that near the equator you had the low pressure, which is because of the warmer temperatures of the air there, and towards the poles you have the high pressure, and in between you have these pockets of small high and low pressure. Okay, why did we have them there? It's basically the adjustment that tends to take place with regards to the temperature of the atmosphere, and nature provides these movements in the form of winds. Now it so happens that while pressure belts and winds happen to be nature's answer to try and attain and balance between variation in temperatures as far as air particles or atmospheric temperature or tropospheric temperature, let us say. The same thing is attempted at when we speak about the hydrosphere. The oceanic waters, particularly the extensive oceanic waters that we understand in the form of these, say, mammoth water bodies by the names of Indian Ocean and the Atlantic Ocean and the Pacific Ocean as well. And to support them, you have the Arctic Ocean and you have the Antarctic, the Southern Ocean. Okay, if I am to mark the Southern Ocean here, this would be the marking of the Southern Ocean. Okay, I'm not still in my hand, but 60 degrees onwards. Okay, all this is going to be your Southern Ocean as such. Okay, this is the Southern Ocean. Let us just keep the Southern Ocean issue a bit aside and try to understand how these ocean currents work. Obviously, we know that towards the equator, that's here, you have a larger insolation, and that insolation gets transferred into the waters of the equatorial regions as well, warming up these waters. So you'll see all those red arrows which mark warm waters near the equator as such. And all those cold arrows which mark the cold waters are seen towards the poles, okay, here as well as here as such. And just like we had these pressure belts and warm air currents moving from the equatorial regions to the poles, similarly, you will see that waters make an attempt to move from the pole to the equator and equator to the poles. And in this process, they develop what are called as warm waters and cold water currents as such, or warm ocean currents and cold ocean currents as such. Now, is there a pattern in which these ocean currents flow? Definitely, there is a pattern you can see, and I will just name you this pattern as such. We'll take one particular ocean and try to see these patterns, and if possible, we'll try to apply those patterns to the other oceans also. What you see as pattern is, let us start moving from the equatorial region. This is the equatorial line. This blue line is the equator. Okay, you'll see that to the north of the equator, you have these warm arrows moving towards the north, and towards the south of the equator, you have these, say, warm arrows moving towards the south as such. Okay, these arrows will move up to the mid latitudes and all the way up into the temperate latitudes also. Okay, and the same way here as well. Now, what do you understand out of this? Okay, the first lesson is that in the tropical regions, that warm waters flow along the eastern margins of continents? Okay, my statement is warm waters flow along the eastern margins of continents in the tropical regions. Uh, can we say so? Yes. Okay, these are warm waters. This is the warm water. This, of course, is the warm water. This is warm water. This is warm water, and this is warm water. So, in the tropical regions, the eastern margins of major continents will have warm ocean currents. So now you don't have to by heart these ocean currents and which of them is warm and which of them is cold. It is, of course, by hearting them is not a part of your syllabus, but even if you wish to, you don't have to. There is a definite logic as to which one is going to be warm and which one is going to be cold as such. Now, as against this, let me also tell you that as far as the eastern margins of, sorry, just a moment. The eastern margins of the continents in these regions, this is it. Okay, the eastern margins will have colder waters in the temperate region. This is cold. Okay, this is cold. Okay, this is cold. Now, in the southern hemisphere, we don't have that much amount of land to obstruct the movement of water. Okay, so you will not have many, for an exception of the South American continent. Okay, you don't have much land in the temperate regions of the southern hemisphere. As a consequence, we have just a few examples to show that the eastern margins of continents in the temperate regions have cold ocean currents. Okay, the Labrador is one here, the Oyashio one here, and then you have this current here as well. Okay, so this is another observation that we can make. Then the next observation that you can speak about is that in the tropical regions, the western margins of the continents will have cold currents. Okay, I can show you. One is here, the Canary current, the Venezuela current is here. Both of them western margins in the tropical regions. The California current, the Peru current. Okay, both of them western margins of the tropical regions as such. Okay, so you'll see that there is a definite arrangement. Okay, there is a science behind the flow of these ocean currents from one region to the other, and there is no reason why we should actually be by hearting these as such. As far as we know, these currents, okay, are there. We should be in a position to understand. Now, While we have looked into one of this logic, what we need to state into the other logic also. Why is it? Okay, the source of this, okay, the source of all this happens near the equator. It starts from the equator, let me tell you. And you'll see that all these arrows on the equator are actually flowing from your right hand side to the left hand side. That means they are flowing from the east to the west. What initiates this westward direction of these warm waters along the equator? Let me tell you that this is the rotation of the earth. And the earth rotates from the west to the east, you'll see that objects on the surface of the earth, particularly oceanic waters, tend to be deflected from the east to the west, and that actually originates the ocean currents. If the earth would not have been rotating, okay, a hypothetical condition wherein the earth would not have been rotating as such, what would have been the conditions? Uh, Whether we would have had these ocean currents, we possibly would still have had these ocean currents, but then the drift caused by the equatorial currents, as you can see in front of you, would not possibly would not have been there as such. Okay, it's a very interesting hypothetical condition that we could imagine and work on as to whether if the Earth would not have been in rotating around its axis, would it have still initiated the equatorial current, and would in that case would have led to the movement of all these currents as such. Now, the further logic is that these westward moving currents from the equator, you'll have two of them. You have one to the north of the equator, north equatorial current, and you have one to the south of the equator, south equatorial current in each of these oceans. Okay, it's not exclusive for any one as such. You'll have them in each of these oceans as such. Okay, you'll see that you'll have them in Indian Ocean also, and you have them in the Pacific Ocean also. They move towards the west. They get obstructed by the water bodies. Okay, sorry, they get obstructed by the land masses as such. The Atlantic currents, you'll see that they get obstructed by the massive landmass of South America. In the uh, Indian Ocean, you'll see that it tends to be obstructed by the eastern coast of the of the African continent, and these islands around Indonesia do obstruct the movement of waters of the Pacific Ocean. This obstruction leads to the deflection of the direction of these ocean currents towards the north and the south, respectively, in the northern hemisphere and the southern hemisphere as such. They move up where they get, say, uh, they confluence, I would say, with the cold currents which are brought in from the uh, polar regions as such, particularly the northern hemisphere. You have the Labrador current moving along, say, the coast of Greenland and northern Canada as such, and then you have the Oyashi current, which comes towards Japan as also as such. An interesting thing is these warm waters. Okay, these warm waters. We know that anything warm is going to be less dense, and anything cold is going to be more dense. So, for example, if we take this portion here, okay, this portion here, when the Labrador current is going to flow like this, and the so-called Gulf Stream warm current is going to flow like this, they will confluence here, but the warm Gulf Stream current will still flow further. It will not flow this way now. It will be pushed into this particular direction, where it carries on as what is called as the North Atlantic drift. The importance of the North Atlantic drift is these warm waters will keep these borders, okay, these coastlines of, say, the European continent, free of very cold temperatures for a significant period of time. It will travel all the way around this and all these coastlines, okay, England, etc. Even in deep winters, you'll see that they don't experience very cold temperatures because of this continuous flow of this warm water of the North Atlantic drift along this. Yes, sir. Yes, it goes towards the poles where it's going to cool down, and then it's going to return back as the East Greenland current also. So that is how these currents move. And we also have studied in economic geography. We would be rather, if you have not earlier, that these points where the warm and the cold currents meet are known as major fishing grounds of the world. This is one. This is another one as such. And then you have one towards Japan as well. Okay, this is where you're going to have these major fishing grounds of the world. These are the best fishing grounds. Not that you don't find fish in other parts of the world, but these are the best fishing grounds of the world as such. Okay, these are a few things that we need to understand as a logic as far as these ocean currents are concerned. A few more logics that we need to understand is while this water is going to move, let me change the ink so that now we can understand it further well. Okay, you'll see that the waters keep on moving in a circular motion. It will start from here and it will come here. Okay, this will start from here and it will come here. Okay, it will start like this and it will come like this. Okay, it will move this and this. Now, why I drawing these? Say it will move from here, come back here, and complete circle. So every ocean, with an exception of that Atlantic Ocean, you see that they complete a cycle sort of a thing. These cycles, okay, these circular movements are called as gyres, Gyres. These gyres play an important role. These are those small storms that you have. That I know I used to do this when I was small. When we go for a bath and we are just watching the waterfall in the bucket as such, we are so very tempted, and many a times actually we just turn those say take a few circles of our hand or finger in that, and we try to develop this as a part of a small sort of entertainment as we develop those small swirls. Okay, you'll see that on the surface of the earth also nature plays this funny thing with us, and you have these gyres in each of these oceans. What is important to note here is that these gyres are in a clockwise motion in the northern hemisphere, and in the southern hemisphere they are in a anti-clockwise motion as such. These clockwise deflections and anti-clockwise deflections are known as what is called as the Coriolis force. Coriolis force. You can go to YouTube. Actually, we could have done this in climatology, but then we are short of time, and that's why I'm suggesting that you could go to YouTube, type Coriolis, Coriolis, Coriolis force, and you'll have these explanations of what exactly the Coriolis force means. If you don't get it and you want it, you still want it, you could remind me at some point of time next semester where I could explain you what the Coriolis force is. This was another fact that we need to understand as far as ocean waters are concerned. And the last fact that we need to understand here is this arrow here. I don't know how many of you all have seen this. Let me bring it to your notice now, because sorry, yeah, because you'll see that you have the northern equatorial current, you have the southern equatorial current, and you have a flow which flows in between them back towards the east. Okay, not all waters deflect to the north and deflect to the south as such. Some of the waters gets pressed between these two and moves into an equatorial along the equator towards the east as such. You will have a similar small current here also. You will have a similar small current here also. Okay, however, this current in the Pacific Ocean is very dominant, and we are going to see what it later reflects into. This is called as the counter equatorial current. Counter equatorial current. Okay, so I think we are now are understanding most of these currents as such. Okay, now just as you would have then a counter equatorial current moving towards the east, you should technically have a counter polar current which is going to move towards the west as such. You will not have that, however, in the northern hemisphere because you have a lot of land in the northern hemisphere. However, you will see that towards the southern hemisphere, you have this current here, the west wind drift, the east wind drift as such. This is one more reason why uh, oceanographers have identified, say, the Southern Ocean as such. What you can interestingly see here, I don't know again how many of you all have been observant enough and have actually uh, marked that if once again I draw the boundary of the Southern Ocean here, 60 degrees latitude, what you see is very interesting. To the north of the 60 degrees latitude, you see a west wind drift. This is the west wind drift. The westerlies will blow, make the waters flow in this particular direction. Though the westerlies are very strong here, you'll see that to the south of the, say, the boundary of the Southern Ocean, you have these arrows which are moving the other way, which is called as the east wind drift. Possibly one of the major reasons why the requirement that the Southern Ocean needs to be classified, because this movement is very interesting, and that's why we need to classify them. Okay, and in fact, if you remember, when we are speaking about the spheres of life, and we spoke about atmosphere, hydrosphere, and the lithosphere as such, we also said the importance. We spoke about the importance of cryosphere for the last 20 years. Okay, the cold study of cold regions and cold temperatures. No wonder the Antarctic continent and the waters around the Antarctic continent are so very significant. And not only that, cryosphere would mean studies of this particular area, the Himalayas as well. And cryospheric studies would include studies of Greenland and around as such. They play an important role as far as climate change is concerned. And as a consequence, all put together, it becomes equally important that as we have studied the lithosphere and the atmosphere, it is equally important that we study the hydrosphere as well. With this information, and if you don't have any further queries as such, I would go further. I think my battery is falling down. I need to get my cables, power cables, which I was carrying to the college yesterday. I'll have to pull out the power cable and I have to switch it on. Just give me a couple of seconds that I actually set up the power connections as far as my laptop is concerned. And we are done. Okay. As I said that it's very important that we understand the importance of this particular career. Okay, this is to do with a very interesting, important current, which is known as the El Nino. Okay, and the El Nino has a huge significance with regards the Indian monsoon also is concerned, because it is believed that the year of the El Nino leads to lesser amount of monsoon intensity as far as the Indian subcontinent is concerned. And that's why we are always afraid of an El Nino year as such. Now, what exactly is an El Nino? I will just give you a very brief idea as to how and what exactly is the El Nino as such. Okay, in an El Nino year, you'll see that you'll have a warmer winter as far as the North American continent is concerned, and you'll see that the easterly winds weaken. Okay, you'll see that these easterly winds weaken towards the South American continent. Um and in a normal year, you'll see that you have these colder waters here, and you'll have these warm waters moving here, and as a consequence, you'll have a strong monsoon here as such. Now, what exactly is the difference between a normal year and an El Nino year? I'll just get you back to these things. Okay, what do you see in a normal condition? You see a cold current across the coast of the western coast of South America. This is the normal condition. what exactly happens is at times, this warm counter equatorial current pushes its way through these two currents and it occupies this space here. The year that it occupies this particular space here is called as an El Nino year as such. Okay, you can see here what has happened. You see that the counter equatorial current has moved all the way here and it is pushing its way here. As we have said that this is going to be warmer and that is going to be less dense. Okay, you'll see that it will override the cold Peru current, okay, which is going to be denser. Okay, so the denser things will go down and the warmer will come up and it will stay above this region as such. And the year this happens, there are cycles, but the year this happens, that's called as an El Nino year. Because this occurrence takes place around December, okay, last week of December, it's called as El Nino because El Nino is supposed to be the child of Christ. There is an interesting mythological story that goes around this coast of Peru. Maybe at some other point of time, we can come back to that. But the important aspect is that we need to have, as Indians, we need to have a normal condition as far as these currents are concerned, because the year of the El Nino is going to be a difficult year as far as Indian monsoon and effectively the Indian agriculture is concerned. So lesser El Nino years, the better, I would say, as far as the Indian subcontinent is concerned. The Peruvians have also actually will also partially dread the El Nino. At times, you'll see that they're happy about this El Nino, and that's why it's called as the child of Christ as such, El Nino. Okay, because it comes up in the last week of December as well. Okay. Anyway, so that's about the impact of oceanic currents and a specific current that evolves, which we tend to study as the El Nino year as such. Okay, having said this, we come back to one of those diagrams I think we have done at an earlier point of time. And what is this diagram about? This is called as the hypsographic or the hypsometric curve. Also, it gives you the various differences as far as land and water bodies on the surface of this planet. This is a more, I would say, a geometric representation, a mathematical representation, a quantitative representation of what we have actually on the surface of this planet as such. Okay, what all do we have on this? Okay, you'll see that the total area, okay, the total area of land on this surface is 139 million square kilometers. Let me just give you a comparative figure that the total area of India is 3.2 million square kilometers. India is 3.2 million square kilometers. The total land on the surface of this planet is 139 million square kilometers. Okay, and the total area of the Earth's surface is 500. That makes this only around 20-21% as such. And the total area of the oceans is 360 million square kilometers as such. Okay, these are a few facts that we need to understand on our way to trying to understand the hypsographic curve as well. The average elevation of the Earth's surface, the average elevation of the Earth's surface is 2,000 meters. Okay, so if you take all the top points and bottom points on the surface of this and we average out it, it will actually be below mean sea level, 2,000 meters below sea level. Okay, so you can imagine the amount of land which is below sea water as such. Then the highest mountain on this planet, of course, we can say is in Asia, and that of course is in Nepal, and that's the Mount Everest. The point is at 8,848. Scientists now put it at 8,850 meters also. The lowest point on the surface of this planet is amongst those oceanic trenches. It's in the Pacific Ocean, the Mariana Trench, which is 11,000. That's taller than the Mount Everest, I would say. Around 2 kilometers taller than the Mount Everest on the surface of this planet as such. Okay, we all have around 29% of the surface made up of land, 71% made up of water. As I've already said, the lowest point is Mariana Trench, and this is in the Pacific Ocean, 11 kilometers. And of course, the topmost point, I don't see they have written it here, but we all know that it's 8850, the Mount Everest. Okay, and you'll see that if we while we have said that the average of the Earth's surface total is this, you'll see that as far as the average of water and land individually would be different. You'll see that this point, which is just above the mean sea level, some say 500, 600 meters above the mean sea level. And this point is the average depth of the water exclusively, only water. This is water plus land. 2000 meters is water plus land. Only land is 841 meters, and only water is 3800, or you could say 3900, or even you could round it up to around 4000 meters as well. Okay. So these are a few facts that we need to understand as far as the depth and the elevation making up the hypsometric curve on the surface of this planet as far as distribution of land and water is concerned. I probably have one more of these for us, a more simplified version, I would say, of the hypsometric curve. It records the same information that we have seen in the earlier diagram. All we have to do is just revise it once again. 500 million square kilometers is the total area of the surface of this particular planet. Of this, you'll see that land area is around 140 million square kilometers. And you'll see that as far as the ocean areas is concerned, it's around 360 million square kilometers as such. The highest point on the surface, now you'll see a change here, 8850. The earlier one was 8848 as such. And as far as the deepest point is concerned, it is 11,030 meters only as such. The average elevation on land around 850 meters. The average depth of waters is around 3,800 meters. The average elevation of the Earth's surface, okay, the whole of the Earth's surface is minus 2,070 meters as such. Okay, so a very simplified version of all that we had done in the earlier diagram. The same one represented here. A revision of that has been taken up, and when we move to the respective hemispheres, looking at these hemispheres not sideways but from the top as such, this is how the northern hemisphere would look like, and this is how the southern hemisphere would look like if we are looking at them from the respective poles as such. What can be observed here is that barring this portion, which is going to be the Pacific Ocean, you'll see that a lot of land can be seen as far as the northern hemisphere is concerned. This, of course, is there, but Atlantic Ocean relatively small as compared to the Pacific Ocean. As against this, you'll see that as far as the southern hemisphere is concerned, you have the Antarctic continent in the center, and you have the southern portions of the African, the South American, and of course the Asian continent, rather the Australian continent exclusively. And the rest of the area significantly tends to be occupied with a lot of water as such. And that's why you'll see that the northern hemisphere is also called as the land hemisphere. And in comparison to that, the southern hemisphere is always referred to as the water hemisphere also. Okay, this was the sheer purpose of this particular slide as such. This is another graphical representation of how the oceans and the land surfaces actually distribute themselves through the various latitudes as such. Okay, you'll see that on the x-axis, let us say here, sorry, on the x-axis here, you have this particular unit, which is say millions of square kilometers. Okay, And then these are the latitudes as such: 0 to 15 south and north, 0 to 30 north and south, 45 north and south, 60 north and south, 75 north and south, and so on and so forth. And this side we'll take it later, the mean annual temperature range as such. Okay, what we can see here is obviously the fact that the oceanic waters do occupy nearly 79%, but land surfaces occupy only 21% as such. But this distribution, as we have already said earlier as well, that is different in different latitudes in respective hemispheres. This at times is also called as an antipodal arrangement. Now, what does this antipodal arrangement mean for us? You will see that if we start from the poles, okay, the northern pole has water while the southern pole has land. One observation. The second is that while the latitudes between 30 and 60 approximately have a lot of water in the northern hemisphere, a lot of land, sorry, in the northern hemisphere, you don't have that much amount of land in the southern hemisphere as such. Okay, this is called as an antipodal arrangement. Now, whether there is some physics behind this remains to be seen. We would not be going into those details, but say geophysicists or those physics scholars who would be learning, trying to understand the processes on the surface of the earth using physics would be really trying to understand these things as such. Okay, a few, I would say, mathematical, or I would say informative points here would be that around 0 degrees to, let us say, a couple of degrees north here, okay, you have maximum amount of water along this particular latitude. Maximum amount of water. Let me change the ink of this. You have maximum amount of water along this particular latitude, or this could be, if this is 0 to 15, then this possibly could be 7. So around 2 degrees, 3 degrees north. Similarly, around 50 degrees south also, you have maximum amount of waters as such. Okay, having said that, okay, you'll see that near Antarctica, you have minimum amount of waters here as such. Okay, because it's all land as such. Okay, on the other hand, you'll see you have minimum amount of land along this latitude. This latitude is along 61, 62 degrees of south. Minimum amount of land is around that. You can check this on the world map as well. As far as land is concerned, maximum amount of land is seen around 45 degrees. 45 degrees maximum, 60 degrees minimum. Let us see if we can confirm that somewhere. And yes, we can confirm it here. Possibly, yes. 45 degrees maximum land. Yes, this is 45 degrees. Let me see. This is 45 degrees maximum land. Okay, what did we say minimum land about minimum land? This is somewhere around 60 degrees, 62 degrees south. 62 degrees south is going to be here. Minimum amount of land around this area. Isn't this interesting for us? Okay, then maximum amount of water is around 0 degrees north. Let us see 0 degrees north. Okay, this is water, this is water. This Indian Ocean section adds to that, and that's why you have a lot of water here. And minimum amount of water around this here because of this extensive Antarctic continent. As such, uh, these are a few interesting facts that we need to understand before we go to the next. As such, this is the distribution as such, but uh, we will stop here right now for this lecture at least, and we will be back at around 9:30 to understand the rest of the aspects as far as oceanography is concerned. I hope you all are following, you have been following what I have been speaking and discussing about for the last 50 minutes or so. I would request you all to put in your names as far as the chat box is concerned, as a matter of your attendance as such, before I switch off the recording, so that I actually would have an official record of the students having attended this particular lecture as such. Now, for the next couple of moments, if you have any queries, you could just unmute yourself and ask me your queries regarding the lecture we have conducted till now. Any queries, please? Well, if you don't have any queries, I will just switch off the recording for this lecture right now. And